Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my uh, introduction to the types of programming languages for people who have already been studying C++. Okay, so why be interested in other programming languages? Well, if you look at the top 10, um, you'll notice that it's constantly changing. July 2021, there was a different top 10 list, though it was very similar. July 2022, the top 10 list is got Python in first place, C in second, Java in third, C++ in fourth, and C# in fifth place. And you can keep reading if you want. Notice that four of those, C, Java, C++, and C#, are in the C family. That is, they have C-like syntax. So you can feel good about the fact that you've learned C++ in my programming class because that will make it very easy for you to write code in C or Java or C# if you need to. Python, on the other hand, is a completely different animal, to mind the pun there. It's actually named after the Monty Python comedy troupe, not after the animal python, but their logo is a little double-headed snake, so it's kind of cute. Python's a completely different animal, and I'm actually going to have another lecture for you to watch on just a general introduction to Python, just so you can see how a completely different programming language works. Okay. When we talk about types of programming languages, the main difference is whether the language is compiled or interpreted. Compiled languages go through this sort of sequence here where you write the source code in an editor, and then you send that to a compiler, which creates something called object code. It's binary computer language code. And then that goes to a linker, which links up your compiled code with all of the libraries that it's trying to import. And then that linker puts out a binary executable file. And when you double click that in Windows or on a Mac or even in Linux these days, or when you type its name in a command line, that binary executable is sent to the CPU and it runs directly on the CPU. It's a series of binary instructions that the CPU knows how to run exactly. And because the CPU is running its native code, it runs fast. An interpreted language, on the other hand, is a little bit simpler in that you have an editor where you write the source code, and then there's an interpreter that translates your source code one line at a time, or even really one token at a time, one piece of a line at a time. And the CPU simply runs the interpreter, so it's running the program as it is interpreted, which is a relatively slow process. Now, on today's modern CPUs that can run at 1 to 4 gigahertz, you may not notice that your interpreted program is running more slowly than a compiled program. But if you have the right level of difficulty in your program, if you've got it trying to do a difficult enough job, then you will notice a little bit of a slowdown in an interpreted language compared to a compiled one. Finally, we have a compromise that two languages, Java and C#, use, where you, again, edit the code, source code in an editor, you send it to a compiler, but the compiler doesn't make CPU-specific binary instructions. It makes what we call bytecode, which is a machine-independent language that can then be run by a virtual machine. Okay, and the virtual machine interprets the bytecode, again, one token at a time, and sends the appropriate commands to the CPU, um, which is slowish. Okay, because it's been compiled ahead of time, it is still faster than an interpreted language, but it's also being interpreted itself in a way through the virtual machine, and so it runs slower than a pure compiled language. So why would you choose one language over another, a compiled language versus an interpreted, for example? Compiled languages are much faster. The compiler is going to check your code for errors before you get to run your program. So while there will still be bugs in your code that slip through, where maybe you typed a 0 where you meant to type a 1 or something like that, the compiler can't check those kind of errors, but it can make sure that you're using the language properly and that your syntax is correct. When you run an interpreted program, because it's checking your code basically, one word at a time or one token at a time, you can get halfway through the run of your program and then suddenly find that you've made a syntax error and the whole program crashes, and because the interpreter does not run through and check your whole program ahead of time. Many a programmer has been burned by writing a program and in an interpreted language like Python and getting half or 2/3 of the way through it and then finding that they made a mistake, and now they have to fix that, and not only fix it but also rerun the program and retype their input, and it can be a laborious process of debugging as you run the program. Compiled code, because the compiler checks your code, it's easier to enforce what we call code safety rules. Things like making sure that the memory that you're using is safe, and you're not putting an integer somewhere where you're supposed to put a character, or putting a double somewhere where you're supposed to put an integer, or overflowing your memory bounds on an array, and you end up crashing the whole computer you're running on. So, the compiler, as it analyzes your code, is capable of checking some of those code safety rules. Finally, the executable, once it's built, contains all the code it needs to run. And I put an asterisk there because that's not exactly true. A lot of modern programs are linked to external libraries that they need to run. They call them DLLs in Windows. They call them other things in other operating systems that you might need code from the operating system to run. You might need code from, if you write a program using Microsoft's .NET system, you need to download and install the .NET system in order for your program to run, because it's linked dynamically to all of those libraries. Okay. On the other hand, interpreted languages also have some advantages. An interpreted language is usually machine independent. If I write Python, a Python program on Windows, and then I take it over to my Mac, it should run exactly the same way. The code can be more flexible. In JavaScript, in a compiled language like C++ or C#, if somebody sends you an object, you need to have that type already defined in your program in order to use it. But in JavaScript, somebody can send you an object over the internet, and you can just create the type for that object, the class for that object, I should say, as the code is running, because it's interpreted. There's no compiler that had to check your classes and their class definitions and everything ahead of time. The interpreted programs are almost always sandboxed by the interpreter. And what that means is, if you remember, if you think back to when you were a little kid and your parent plopped you down in a sandbox and you were playing with your toys, maybe you spilled some sand outside the sandbox, but basically you stayed in that one little area. So similarly, an interpreted program runs inside the interpreter, so it can't hurt the rest of the machine. It can't cause the whole computer to crash the way a C++ program could if it overflows its memory. And finally, in an interpreted language, you can import packages as you go. So I can be running along writing R scripts that handle my statistical data and realize that I need a new package, and I can just sit there and type library ggplot, and it imports that right away. Maybe it didn't even have it installed, so I can install it first and download it from the internet, and while I'm running my program, I can download this package and import it into my program. So that's a handy trick with interpreted programs, and that's one of the things that makes Python and R so popular with data scientists, is that they often find that they need a new package while they're running their program, and they can just add packages to their program willy-nilly. Okay, so here are some examples of each approach. Languages you've probably heard of in the compiled category are C, C++, Java, and C#. I put an asterisk by because, of course, as I said before, those compile to a bytecode middleman kind of that runs on a bytecode interpreter or a virtual machine. Apple's new language Swift that you can write iPhone apps with, and an older language called Delphi, also known as Object Pascal, is making kind of a comeback in terms of it occasionally peaks up into the top 20 languages on the TIOBE index. Interpreted languages, we've got Python, JavaScript, which has no relation to Java except for the name. They are completely different languages. R, as I've said, for statistical computing, and MATLAB for scientific and mathematical computing. These are all interpreted languages. Another way to classify our languages is by syntax. Okay, we have curly brace languages, languages that inherit C's habit of grouping things with curly braces, and as a result tend to have very C-like syntax. We've got C, C++, C#, which is supposed to, according to one source I read, look like C+++++. Okay, you've got an extra level above C++. Java and JavaScript both use C-style syntax. And then Swift I put in there because it does use curly braces, but they've made enough huge changes to the C syntax with Swift that you won't really recognize Swift code as easily if you look at it in a curly brace kind of way. Then there are languages that the authors just invented a unique syntax for that language. Okay, so there's Python, there's MATLAB, there's R, there's Visual Basic, which Microsoft kind of invented the language as it went along. And there's that Delphi Object Pascal, which all five of these attempt to be more readable in their syntax than the curly brace languages. They succeed and fail to different extents in that effort. But like I said, the next lesson, the next lecture, the last lecture I'll give in this course will walk you through a quick tour of Python, and you'll get to see for yourself whether you think that's more readable or not. Okay. Finally, in this little tour of programming languages, I want to show you just some snippets of other curly brace languages here to give you an idea of how they're similar and different to C++. Um, this is a messaging system I wrote for my operating systems class that has three parts to it. There's a C part here, and then there was a Java part that I wrote for operating systems 2, and then there was a C# front end that I made a graphical interface for it with C# or for Windows. So you can see here we've got the pound includes. Okay, looks just like C++, except instead of having angle brackets around the headers, instead of having angle brackets around the system headers, we just have quotes that bring in yams headers.h and string handlers.h. We have a printf function, which stands for print formatted. Instead of strings in C++, we have character arrays, what we call C strings. And I defined a constant called string size that just makes a huge array to hold a string. We have scanf, which stands for scan formatted. And you tell it what it's looking for. In this case, it's looking for %s, a string, and it's going to try to store that in my mailbox name array. We don't have a specific type for a byte in C. So there's a unsigned integer of size 8 that we can use to store a byte. That's an 8-bit entity, which is what most internet communication happens with, is you send and receive bytes at 1 byte at a time. We have a switch, which should look familiar to you from C++ here. I obviously don't have the whole program listed out for you here. We've just got one case. I've got a constant that I defined called syscall ping, and if the system call that I was given is ping, then my byte, I'm going to create a random byte using the rand function, and I'm going to printf that I'm sending code. Now here I'm going %d for decimal, and the decimal number that I'm printing is my random number byte. Okay. And then I can printf server sent response %s, that's a string, and that's my response, which must have been defined somewhere else in this code. Okay, Java looks quite a bit different. We don't have pound includes, instead we have import statements. And all of the things that we import come from the Java library with some kind of almost URL-like syntax, java.util.scanner, java.net.star, java.net.socket, and etc. All of our code in Java is organized into classes. There is no straight, just functions that you drop into your code like you can in C and C++. You have to have a class. And this class is called an RPC server, Remote Process Communication Server. And then we have a whole lot of these things that are called static. Okay, I don't think we introduced that in our object-oriented, or 2 object-oriented lessons in C++. but a static variable exists for everybody in the class. It's kind of a way of creating global variables um, in an object-oriented language. Um, you can see that our RPC server has to have a public static void main function. And Java, C# as well, has something called a try statement, which means we're going to do the following, but if something fails, we're going to have another keyword further down in our code called catch that's going to give us an opportunity to respond to that error so that our program doesn't just crash and burn. There's a way to catch the errors and respond to them, and that's called exception handling. You can see that we print things using system.out.println, and we're just passing it a string here. You can see that we do have a byte type in Java, so that makes it easier to send internet messages 1 byte at a time. Since Java was developed as an internet language, that makes very good sense, right? And finally, you see there is a string type in Java. You can put, here I've got a whole lot of escape characters showing quotes in there, but then there's a plus, and then I put in my get host address here, and that just automatically gets converted to a string because it's been added to a string. That's kind of a cool feature of Java. And then I take my string here and I plus equals another string, and the server port, again, server port gets automatically converted to a string as part of being plussed with other string characters. And you can't necessarily do that in C++. Well, you can't do that in C++. Okay. Here's a C#. In C#, all of our programs live in a namespace. You can have multiple namespaces in your program. Once again, the everything here is a class. We have a class RPN numbers that, in this case, the colon does not mean inheritance. It means it implements something called a interface called iNotifyPropertyChanged. And that means that when you set a value, it calls the property changed function, which lets the user interface know to change the number that's being displayed on the screen. One thing I want to show you is that you can have a private variable here, and then instead of having public get and set functions, what you do in C# is you create a public property, which usually has a capital letter, and it has a get function and it has a set function. You can also create read-only properties like answer string that only has a get function. It doesn't have a set. Another cool thing about C# is that if all you want your function to do is return a value, you can use this equal greater than arrow code to indicate that the function get is going to return answer. The function get down here is going to return answer.toString. Okay. And finally, I wanted to show you just a couple of bits of graphical interface code here. We've got clear button click is a method of the class main window, which inherits from the Windows window. Okay. Um, you can have a plus minus button click. You can have a delete button click. And each of these just has a small change that it makes to our numbers object. It's going to set entry and answer to 0 if you hit clear. If you hit plus minus, it's going to make entry equal negative entry. Or think about a calculator. You hit the plus minus button, that changes the sign of the number. And then a more complicated one, this one actually uses the remote process communicator that this thing is built with. Answer equals rpc stubs.div. That's a function I wrote that takes the answer and the entry. Okay. And you can see here we have standard C code for that inline if statement. If answer is equal to max value, then we've got some kind of error and we'll set answer to 0. Otherwise, we'll set answer to the answer that we came up with. Okay. Those are 3 curly brace languages that should look fairly familiar to you if you've studied your C++. Here's a language that will look completely different, R. If we want to make a pie chart, you make a list by calling the concatenate function C, and then you list your numbers, 8, 7, 5, 3, 7. You can make a list of strings by calling concatenate and pass in glazed, filled, frosted, plain, and other. And then you call the pie function. That's going to create a pie chart. Now, this is a statistical language, so it's got built-in functions for doing all sorts of graphics, pies and box plots and line plots and scatter plots and all sorts of other fun things. So you just call slices as what you're graphing. You tell it that labels is going to equal donuts, that your donuts is going to be the labels. And then you tell it your main title is pie chart of donut variety. You can read data from a file by calling read.table, pass it the name of a file. You can get a summary of the data you just read. And of course, if that data includes columns called math and grade, you can do a plot of math versus grade and get a nice box plot out of that. Finally, we're going to explore the Python language in detail in the next lecture. So take what you've learned from this lecture on different programming languages and hold on to that, and then watch my last lecture on a brief introduction to Python. And when you're done with that, there's going to be a quiz on Blackboard for my students to take, at least. Okay, so until then, good luck and happy programming.